Let's talk about stress. All right, how do reactions respond to stress? Well, they follow something called Le Châtelier's principle. So let's talk about it. All right, so Le Châtelier studied the way equilibria, which is the plural of equilibrium, respond to change or stress. Now, why would he be doing that? Well, he wanted to apply chemistry to industry and get maximum yield from reactions. So if you're trying to produce ammonia, for example, how can you get the most amount of ammonia? Okay, the most bang for your buck. So he was about applying chemistry to industry. So let's review some features of reactions at equilibrium because we need equilibrium for Le Châtelier's principle to even apply. So remember, reactions have to be reversible for there to be equilibrium. So reactions that go to completion, like cooking an egg, like burning a log, can't reverse it, can't reach equilibrium. Only a reaction that is reversible, has a forward and a reverse reaction, those ones can reach equilibrium. Remember, equilibrium is dynamic. That means it is still, like, stuff is still happening. Static would mean nothing's happening. Dynamic means products are being formed, reactants are being formed. The forward reaction is happening, the reverse reaction is happening. But it's happening at the same rate. So it's like the same number of players on the field, but we're swapping in and out, okay? Also, there has to be a closed system. Put a lid on it, not a ring, a lid. You need a lid, you need a lid, you need a lid. You got to close the container. You got to seal it. You can't let things escape. You can't let things come in. You have to have a closed system. The rates of the forward and the reverse reaction are equal. Rates are equal. Rates are equal. Look, it's like equal sign. Rates are equal. Forward and reverse. The rates are equal. The concentrations are constant. Concentration, constant. Concentration, constant. So the amount of product and the amount of reactant stays the same when we're at equilibrium. Remember, I'm still getting products formed and I'm still getting reactants formed, but the amount is staying the same because the rates are equal. The concentrations are constant. So how will an equilibrium respond to stress? So an equilibrium under stress will follow Le Châtelier's principle. So what does that mean? Well, let's find out. So Le Châtelier's principle says a system at equilibrium will respond to a change or stress in a way to get rid of the stress. So systems aren't going to respond in a way that makes the problem worse. They're going to try and fix the problem. Okay, so as you can see in this visual here, we're at equilibrium, stress is applied, and in this case, we distribute the mass and resolve the stress. All right, so let's see what happens in reactions. Okay, so to see what happens with Le Châtelier's principle, we need to disrupt the equilibrium. So, things are out of balance. What happens? Well, the system shifts to either form more products or more reactants. So it's out of balance. So the system is going to adjust. And then get a new equilibrium. So we're at equilibrium, stress. Voila. Resolve the stress. Get to a new equilibrium. So what kinds of stress will equilibria respond to? Well, let's see. First is changes in concentration. So if we have more of a reactant, more of a product, as an example, or less, okay? So changes in concentration, that's one way. So if we increase the concentration, the equilibrium will shift away from the increased concentration. So look at this visual. So I had an equilibrium, and then all of a sudden I added a bunch more of A. And the system is like, oh no, we have too much. So what will happen, I need to use up this A. So the reaction will shift this way. And it will use up the A in the process, but it will also use up B and then make more of C and D until we get to a new equilibrium. So what if instead we increased B? Same thing would happen. It would shift again this way to resolve the stress. Okay, the equilibrium will always shift away from what you increase. So if I increased something on this side, like C or D, the equilibrium would shift this way to the left. So what if you decrease the concentration? Well, equilibrium is going to shift toward the decreased concentration. Like, oh no, we don't have enough, hurry, make more, okay? So for example, if I decrease the amount of H2, the equilibrium will shift toward that side, and I'll start to make more H2, more N2, and we'll be using up NH3. What if, on the other hand, I decreased NH3? Well, the equilibrium would shift this way to the right and begin to make more NH3 and use up N2 and use up H2. So we have a system at equilibrium. Stress, we add more reactants. How do we solve this problem? We need to move some over here, right? So we need more on this side. We have too much on this side. So the equilibrium shifts in this direction. New equilibrium. What if now, all of a sudden I have too many products? Do you see this is off balance? I added too much. So now I need to make more. I need to shift the equilibrium this way. New equilibrium. All right, so with concentration, remember we have a dynamic equilibrium. Reactants are making products, products are making reactants, but the rates are equal. We're in balance. The rates are equal. All of a sudden, if we increase the amount of products, as an example, or we increase the amount of reactants, the equilibrium is going to shift. So if we increase reactants, the equilibrium shifts this way. If we increase products, the equilibrium shifts this way, okay? So we can also change temperature. So we were talking all about concentration. So in order to figure out the effect with temperature, we have to know if it's exothermic or if it's endothermic, okay? And the thing is, it responds exactly the same way as a change in concentration. So what do I mean? Well, if we look here, heat, or it could be listed as kilojoules. That's a common thing that we might see. I look where it is in the equation, and then I act like it's just another reactant or just another product. So for example, in this case, if I increase the temperature, I'm going to shift this way, move away from it, okay? So if it is exothermic, that means energy would be on this side. That is the forward reaction. The reverse reaction is endothermic, and heat is on the reactant side when we're looking at the reverse reaction. Okay, so again, heat is on that side. All right, let's look at this reaction. You can see right here, right about this point. You see before this, the concentrations are changing, and then right here, every single concentration is a straight horizontal line. So that means the concentrations are constant. This indicates at this point we are at equilibrium, okay? And right here, it says the temperature was decreased. So let's see why it responds like this. Well, here's where energy is. That would be temperature. Okay, sometimes it says heat, energy, temperature. That's what we're going to look at. It says that temperature was decreased. When something is decreased, the reaction shifts toward that side. So the reaction is shifting to the right, which means what happens? SO2 is going to get used up. O2 is going to get used up, and SO3 is going to get produced, and energy is going to get produced, so the temperature will go back up. So let's see if in fact that is what happened. What happened to SO2? Look at that, went down. That's what I said. Look what happened to O2, also went down. And what happened to SO3? It went up. Just as I said, that is how an equilibrium responds to stress. It always tries to resolve the stress. We can also change pressure. This only affects gases. Okay, so if there aren't gases, then you don't worry about it. So let's look at this reaction, which is all gases. What matters for this are the coefficients. So I have 2 gas molecules here and 3 gas molecules here for a total of 5 gas molecules on the reactant side. And I have just this 2 gas molecules on the product side. So if I increase the pressure, like itty bitty living space, okay, I want to go toward less moles of molecules, and that would be this side. So if I increase pressure, the reaction favors this side. If I decrease pressure, give lots of room, okay, it's going to favor the side that has more molecules, which in this case would be this side. So with a lot of room, low pressure, this side is favored. When I have less room, high pressure, this side is favored. So if you decrease pressure, it is going to shift toward the side with more gas molecules because you decrease pressure, giving lots of space. Increase pressure, itty bitty living space, less molecules can fit. We can also add or remove a catalyst. Now, in reality, a catalyst has no effect on equilibrium. All it does is speeds up both the forward and the reverse reaction. So we actually get to equilibrium faster, but it doesn't actually change the equilibrium, okay? So you can see when you have the catalyst, you can see how much more quickly the concentration is changing. So we reach equilibrium sooner, but it doesn't change the point, the concentrations where we have equilibrium, okay? So what does adding a catalyst change? It changes something called activation energy. So you can see we need less when we have a catalyst. So here's a quick summary. The stresses, we can increase concentration, we can decrease concentration, we can increase and decrease pressure, we can increase and decrease temperature, and we can add a catalyst. So when we add Na2SO4, okay, so it says what occurs when Na2SO4 is added to the system, increasing the concentration of this. So here's this substance, I'm increasing its concentration. What happens when I increase concentration? The equilibrium shifts away from that side. So it is going to shift to the left, to the reactant side. When it shifts to the left, what happens? This amount goes up, this amount goes down, and this amount goes down. So let's see, we just said it shifted to the left. So that means we can get rid of these two. Stop reading those. We know they're not right. And what did we say happened to BA? It went down. So there we go. All right, here's another equation. Increasing the temperature causes concentration. Okay, so temperature. Where's temperature? It doesn't say temperature, but it says this. Increasing temperature. When I increase something, the reaction shifts, the equilibrium shifts away from it. So that means I'm going to start using this up. I'm going to start using this up. I'm going to start using this up, and I'm going to start making this. So what happens? H2, oh, nope, didn't increase. Nope, H2 isn't constant. HI isn't constant. Oh, HI is increasing. All right, which term identifies a factor that will shift a chemical equilibrium? Temperature. Remember, a catalyst just makes you get to the equilibrium faster. It doesn't actually shift the equilibrium. Okay, so here's another reaction. Which change will cause the equilibrium to shift? Well, you see one is pressure. Do you see any gases here? Negative, so pressure is wrong, okay? Does a catalyst cause a change in equilibrium? No, we just get there faster. So the two that are left, what's the right answer? Temperature, right? So if I increase temperature, the reaction would shift this way. If I decreased temperature, the reaction would shift this way. All right, here's another equilibrium. What changes occur when the temperature is decreased? So where's temperature? Energy. Decrease it. What happens? Equilibrium shifts toward the side where you decreased. okay? So that means if I'm shifting this way, I'm going to start using this up, increasing this, and increasing this. So is H2 decreasing? Yes. Is NH3 decreasing? No. Is H2 increasing? No. Is H2 decreasing? Yes. Is N2 increasing? No. Well, okay, hopefully this one is right. H2 is a decreasing? Yes. NH3 increasing? Finally, there we go. And that is how reactions respond to stress, Le Chatelier's principle. I hope you learned something new today.